Welcome to this video in which we will discuss some common used design approaches for FAR filters. The frequency response of an nth order causal FAR filter is given by the shown equation, and the design of an FAR filter involves finding the coefficients hk that result in a filter response that satisfies a given set of filter specifications. One of the most important advantages of an FAR filter over IAR filters is that FAR filters can be easily constrained to have exact linear phase. In a previous module we've seen that such FAR filters preserve the wave shape of the input signal and that exact linear phase can only be achieved with even or odd symmetric impulse responses. Because FAR filters are generally designed to have linear phase, we consider the following three design procedures. Based on the Fourier transform for discrete-time signals and windowing, based on Equiripple filter design, and finally based on frequency sampling. Assume that the desired ideal low-pass filter response HD with cutoff frequency theta c is known as depicted in the figure. Using the inverse Fourier transform, we can determine the infinite length non-causal desired impulse response HDN. In the window method, a finite length FAR filter is obtained by multiplying this desired impulse response with a finite length window Wn to obtain a finite duration impulse response Hn. The time domain window Wn can be represented in the frequency domain by Wejθ, while the multiplication operation in time domain is represented in the frequency domain by a convolution, which results in the non-ideal frequency response Hejθ that is obtained as the convolution result of the ideal frequency response with Wejθ, which results in a smoothest version of the ideal frequency response. In the following slides we will show that there are different types of windows that may be used in the window design method. We will also see that how well the non-ideal frequency response approximates the desired ideal frequency response is determined by the width of the main lobe of Wejθ and its side lobe peak. In the ideal case, the main lobe width should be extremely narrow, approximating a delta pulse. As a final step, the finite length non-causal impulse response Hn can be made causal by shifting it in such a way that all impulse response indices are greater or equal to 0, represented by the causal impulse response Hcn. This shift operation causes a linear phase change of all frequencies of the filter Hejθ. The left-hand figure shows the time domain representation of a rectangular window of length 32 samples. The right-hand plot shows the frequency representation in which the magnitude is denoted on dB scale. Some other commonly used windows are Henning, Hamming and Blackman windows. All analytical expressions of these windows are available and can simply be used to calculate the coefficients Hn as the product of Hdn multiplied by Wn. Kaiser developed a family of near-optimal parameterized windows. However, since the concept of the filter design method is the same, we will not go into further detail of the Kaiser window. As mentioned before, the window design method is determined by the following two most important factors of the window: the main lobe width delta and the amplitude A of the side lobe peak. Ideally, the main lobe width delta should be narrow and the side lobe amplitude A should be small. The causal FAR filters obtained by simply truncating the impulse response coefficients of the ideal filters, exhibit an oscillatory behavior in their respective magnitude response, which is more commonly referred to as Gibbs phenomenon. Some general properties of WE⁻ theta are the time bandwidth product m multiplied by delta is constant, which implies that the main lobe width delta can only be made smaller by increasing the length m of the FER filter, and thus the price to be paid is increasing complexity. As follows from the previous slide, the side lobe amplitude A does not depend on the length m, but on the window shape. Usually, a smaller side lobe amplitude A results in a wider main lobe width delta. Finally, note that the main lobe width delta is directly related to the transition band. Suppose that we would like to design an FER linear phase filter according to the specifications as depicted in the figure, with cutoff frequency theta c is 0.2 pi, which is in the middle of the passband and the stopband cutoff frequencies theta p and theta s respectively. Because the specifications calls for a transition width of delta is 0.02 pi, it follows from the characteristics of a Henning window that the required filter order should be 310 samples long, and thus the impulse response has to be delayed by 155 samples to make it causal, which is reflected in the equation of the impulse response weights. Furthermore, for a stopband attenuation of 20 log 0.01, which is equal to -40 dB, we use a Henning window, which can be used to window the impulse response weights. Although we could also have used a Hamming or a Blackman window, these windows would over-design the filter and produce larger stopband attenuation at the expense of an increase in the transition width. The two shown plots show the values of this impulse response and the magnitude response in dB scale. A more detailed zoom-in of the passband is depicted in the right-hand plot. The design based on FTD and windowing is simple and it generates results in a filter with relative good performance. However, these filters are not optimal in two respects. First, the passband and stopband deviations, delta p and delta s, are approximately equal. Although it's common to require the stopband deviation delta s to be much smaller than the passband deviation delta p, these parameters cannot be independently controlled in the FTD and windowing design method. Therefore, with the FTD and windowing approach, it's necessary to over-design the filter passband in order to satisfy the stricter requirements in the stopband. Second, for most windows, the ripple is not uniform in either the passband or the stopband, and generally decreases when moving away from the transition band. Allowing the ripple to be uniformly distributed over the entire band would produce a smaller peak ripple. Parks and McLellan developed an iterative optimization algorithm with which these problems are solved. This algorithm is implemented amongst others in MATLAB. The equation gives a rough estimate of the filter length. For the same example as on the previous slide, this Equiripple filter design approach leads to an FER filter with m is 185 weights, which is much less than the 310 weights that were needed for the FTD and windowing approach. Another method for FER filter design is the frequency sampling approach. With frequency response h(e⁻j theta, which is the FTD of the length m FER impulse response hn, and hk, the m DFT coefficients, we have seen in the module about special filter structures that the frequency sampling filter parameterizes the desired frequency response h e to the power j theta at m uniformly spaced frequencies between theta is 0 and theta is 2 pi by the m DFT coefficients hk. Note that in this approach both the impulse response hn and the DFT coefficients hk are periodic sequences with period m. In practice, this approach is used to implement narrowband filters, in which case most of the DFT coefficients are equal to 0. In such cases, the filter is not implemented as a transversal filter with m weights, but it's implemented very efficiently as the depicted cascaded parallel structure in which the weights alpha L denote m uniformly spaced poles on the unit circle. As an example, let's design a low-pass filter based on frequency sampling by predefining the frequency response h e to the power j theta at ms33 uniformly spaced frequencies between theta is 0 and theta is 2 pi. Thus, we use an 33-point DFT and we defined the DFT coefficients hk equal to 1 for indices in the range k is 0 until k is 8 and k is 25 and k is m-1 is 32, and hk is equal to 0 for all other indices k. The phase is 0 for all indices k. Remember that the frequency indices k represent uniformly spaced frequencies between theta is 0 and theta is 2 pi. Thus, the cutoff frequency of the low-pass filter is in between the frequency index k is 8 and k is 9, which is approximately equal to theta is pi over 2. By applying the 33-point inverse DFT, we obtain the ms33 weights of the FER impulse response Hn. We can check the approximation of the frequency response by applying the FTD to the depicted ms33 weights of the impulse response Hn. The left-hand side figure and the figure in the middle now also show the magnitude response in red and the phase response in blue, both as a function of the continuous frequency theta, in the range theta is 0 and theta is 2 pi. From these figures it's clear that the frequency response h e to the power j theta of the designed filter only equals the predefined values hk at the ms33 uniformly spaced frequencies between theta is 0 and theta is 2 pi. Furthermore, it can be seen from the phase response in blue that the filter is not a linear phase filter. This follows from the fact that the impulse response Hn, as depicted at the right hand side figure, is not symmetric around the center point n=16. By applying a phase shift to the DFT coefficients hk, the impulse response Hn can be made symmetric around the center point, which will be shown in the next slide. Based on the design of the same causal low-pass filter with cutoff frequency theta c approximately equal to pi over 2, but now with linear phase, the design procedure of the frequency sampling approach contains the following basic steps. Define the frequency response h e to the power j theta on m uniformly distributed points between theta is 0 and theta is 2 pi, and take care of the phase shift in order to obtain a linear phase filter. To verify, the impulse response Hn of the FER filter can be calculated via the inverse DFT, which results in a symmetric function around the center point at n=16 in this case, and the shape represents a sampled Dirichlet or sink-like function, which is indeed the inverse Fourier representation of a low-pass filter. Finally, The filter can be implemented with the cascaded parallel structure as depicted on one of the previous slides. The FTD of the m weights of the AVR impulse response Hn is depicted in the plots. From this it follows that this method only guarantees correct frequency response values at the points that was sampled. This sometimes leads to excessive ripple at intermediate points. For this reason, the design can be refined by predefining the frequency response at more uniformly spaced frequencies, especially to make the transition step smaller. This ends this video in which we discuss some AVR filter design approaches. Thank you for your attention.